the walls remain. It heals itself. The speed cost us everything. Venice is sinking. What are we building that anyone will care about in 900 years? Archaic resilience.
Chapter 1. The Wall That Refused to Die. Northern England, 1987. A conservation architect named Gerard Lynch stands inside a partially collapsed barn on the Yorkshire moors, and he cannot understand what he is seeing. The barn itself is unremarkable, a standard agricultural structure built sometime in the 13th century, abandoned for at least 200 years, its roof long gone, and its wooden elements rotted to nothing. But the walls remain, not just standing, thriving. Lynch presses his palm against the interior stonework and feels something impossible. The joints between the stones are not crumbling. They are not powdering under his touch the way every 20th century mortar joint does after a few decades of exposure. Instead, they feel almost eat. He scratches the surface with his fingernail and produces a white powder, calcium. He realizes he is looking at mortar that has spent 700 years exposed to rain, frost, wind, and the relentless chemical assault of Yorkshire's acidic moorland air. And it is harder now than when it was first applied. This is not preservation. This is not stasis. This is a material that has been actively strengthening itself for centuries. Lynch will spend the next 30 years of his career trying to understand why. He will become one of the world's foremost experts on historic mortars. He will train hundreds of conservators in techniques the construction industry abandoned over a century ago. And every conclusion he reaches will point to the same uncomfortable truth. We stopped using lime mortar not because we found something better, but because we found something faster. The speed cost us everything. Chapter 2. The Chemistry of Transformation. Lime mortar begins as limestone. Calcium carbide, the compressed remains of ancient sea creatures piled miles deep on prehistoric ocean floors. The limestone is heated in a kiln to temperatures exceeding 900 degrees Celsius. At this temperature, a chemical transformation occurs. The calcium carbide molecules release carbon dioxide, leaving behind calcium oxide, a caustic white powder medieval builders called quicklime. Quicklime is not a building material. It is a weapon. Contact with water produces an explosive exothermic reaction, generating temperatures that can ignite dry wood and cause severe chemical burns to exposed skin. Medieval lime burners worked one of the most dangerous jobs in the construction trade. Many carried scars, some carried blindness, but quicklime, for all its violence, is only an intermediate stage. When mixed carefully with water, a process called slaking, the calcium oxide transforms again, becoming calcium hydroxide, known as slaked lime or lime putty. This substance is alkaline, white, smooth, and utterly workite. Mixed with sand in ratios perfected across 40 generations of trial and error, it becomes lime mortar, a paste that can be pressed between stones and will, over time, transform itself into something very close to the limestone it originally came from. This transformation is called carbonation. The calcium hydroxide absorbs carbon dioxide from the air and converts back into calcium carbide, artificial limestone grown in the joints between stones, binding them together with a material chemically identical to the stone itself. The process takes years, sometimes decades, but once complete, the mortar and the stone become a single continuous material. There are no weak points. There is no interface where water can penetrate and freeze and split the joint apart. There is only stone. Chapter 3. The Breath of Centuries. Here is what modern construction science took 200 years to rediscover. Lime mortar breathes. The calcium carbide crystal structure that forms during carbonation is not solid in the way Portland cement is solid. It is porous at a molecular level, riddled with microscopic channels that allow water vapor to pass through without allowing liquid water to penetrate. This matters more than almost any other material property in building construction. All buildings contain moisture. Rain penetrates walls. Groundwater rises through foundations. Human activity, cooking, breathing, bathing, releases water vapor into interior spaces. This moisture must escape, or it will destroy the structure from within. In a lime mortar wall, moisture moves freely. Water vapor passes through the mortar joints, reaching the exterior surface, evaporating into the atmosphere. The wall stays dry. The stones stay stable. The interior remains habitable. In a Portland cement wall, moisture is trapped. The dense cement matrix blocks vapor transmission. Water accumulates inside the wall structure, cycling between liquid and vapor, eventually finding weaknesses, hairline cracks, gaps in the cement surface, interfaces between cement and stone. When water freezes in these spaces, it expands. When it thaws, it contracts. Each cycle widens the cracks. Within decades, cement-pointed walls begin to spall. The stone faces flaking off, the joints crumbling, the structure failing not because the stone is weak, but because the mortar is suffocating it. Medieval builders did not have vapor transmission theory. They did not have moisture meters or building science laboratories. They had observation across centuries. They could see that lime mortar walls stayed sound while other materials failed. They did not need to know why. They only needed to know what worked. Chapter 4. The Miracle of Autogenous Healing. In 2014, researchers at the University of Bath published findings that should have revolutionized the construction industry. They demonstrated, through controlled laboratory experiments and field observations, that lime mortar possesses a property no modern building material can match. It heals itself. The mechanism is elegant. When a crack forms in carbonated lime mortar, from settling, from impact, from thermal expansion, rainwater enters the crack. This water is slightly acidic from dissolved atmospheric carbon dioxide. As it penetrates the mortar, it dissolves small amounts of calcium carbide from the crack surfaces. The calcium-rich water then migrates through the crack by capillary action. When it reaches the exterior surface and evaporates, the dissolved calcium carbide precipitates out of solution, directly into the crack, filling it with new mineral material chemically bonded to the original mortar. The process is identical to how stalactites form in limestone caves. It requires nothing more than rain and time. Medieval builders did not know the chemistry, but they knew the result. They watched walls develop cracks during construction settling, then watched those cracks disappear over subsequent decades. They called lime mortar living stone, not metaphorically, but literally. They believed, with good reason based on their observations, that lime mortar was somehow alive, actively repairing damage the way skin heals a wound. Modern Portland cement does not heal, cannot heal. The chemical structure of set cement is stable, which sounds like a virtue until you realize that stability means permanence of damage. Every crack in a cement structure is forever. Every crack in a lime mortar structure is temporary, waiting for the next rain to begin its repair. Chapter 5. The Castle That Taught Itself to Stand. Bodiam Castle rises from the marshes of East Sussex, like a postcard of medieval England. Square towers, crenellated walls, a moat reflecting gray sky. Built in 1385, abandoned by 1644, it has spent nearly 4 centuries with no roof, no maintenance, no human intervention whatsoever. Rainwater has fallen directly onto its walls for 16 generations. Frost has attacked it through 400 winters. The marshy ground beneath it has shifted and settled unpredictably. By any modern engineering standard, Bodiam should be a ruin. Walls collapsed, towers crumbled, foundations undermined by moisture. Instead, it stands substantially intact. The walls that face prevailing weather show no more degradation than sheltered walls. The joints between stones remain tight. Structural assessments conducted in the 1970s found that the castle's lime mortar had achieved compressive strengths exceeding those of the stone it bonded. The mortar had become stronger than the building material it was designed to support. This is not anomaly. This is pattern. Across Europe, structures built with lime mortar before the 19th century routinely outlast structures built with Portland cement in the 20th. The Lincoln Cathedral has stood since 1092, the Tower of London since 1078. The Pont de Garde aqueduct in France, built by Romans using lime mortar techniques later adopted throughout medieval Europe, has survived over 2,000 years. Compare this to modern concrete structures. The average lifespan of a reinforced concrete building is estimated at 50 to 100 years. Many fail earlier. The concrete itself does not degrade significantly, but the cement matrix cracks, water penetrates, steel reinforcement corrodes, and the structure becomes unsafe. A 2019 report by the American Society of Civil Engineers estimated that 46,000 bridges in the United States are structurally deficient, most due to concrete degradation. Structures built to last forever are failing within decades. Structures built 9 centuries ago require only minimal intervention to remain sound. Chapter 6. The Lime Burner's Fire. The production of quicklime defined entire landscapes across medieval Europe. Lime kilns appeared wherever limestone outcrops met adequate fuel supplies. The chalk downs of southern England, the karst regions of central France, the Dolomite hills of northern Italy. These were not small operations. A single cathedral construction project could require thousands of tons of lime over building periods spanning decades. The kilns operated continuously, day and night, consuming timber and limestone in quantities that shaped regional economies. The lime burner's profession demanded a specific kind of endurance. Kiln temperatures had to be maintained above 900 degrees Celsius, hot enough that the limestone glowed orange-white in the darkness. Fuel had to be added constantly. The fire never permitted to fall below critical temperature. A single miscalculation could ruin an entire batch, wasting weeks of fuel gathering and stone quarrying. Most kilns operated on 3-day cycles. 72 hours of continuous burning, the lime burner sleeping in shifts if he had assistants, not sleeping at all if he worked alone. The heat alone was punishing. Standing near enough to monitor the fire meant enduring temperatures that blistered exposed skin. The dust was worse. Calcium oxide powder, fine as flour, infiltrated everything. It coated the lime burner's lungs, reacted with the moisture in his eyes, accumulated in his skin until his hands cracked and bled. Life expectancy in the profession rarely exceeded 50 years, but the product was essential. Without lime, no mortar. Without mortar, no cathedrals, no castles, no stone bridges, no city walls. The lime burner occupied the lowest rung of the construction hierarchy. Poorly paid, rarely mentioned in records, his contribution invisible in finished buildings. Yet without him, medieval civilization could not have built in stone at all. Chapter 7. The Sand That Mattered. Lime putty alone is not mortar. It requires aggregate, particles that provide bulk, prevent shrinkage cracking, and modify the final material's properties. In medieval practice, this aggregate was sand. But not all sand is equivalent. The shape of sand grains determines how they pack together and how well the lime binder adheres to their surfaces. Round grains, typically produced by water erosion in rivers and beaches, pack inefficiently and provide poor mechanical bonding. Angular grains, produced by crushing rock or found in glacial deposits, interlock with each other and present rough surfaces for lime adhesion. Medieval masons preferred pit sand, material dug from inland deposits where glacial action had fractured and tumbled particles without the smoothing effect of water transport. The best pit sand contained a mix of grain sizes, from fine powder to coarse grit, allowing smaller particles to fill spaces between larger ones and creating a dense, strong matrix. Beyond shape, sand cleanliness mattered critically. Organic material, decomposed vegetation, insect remains, anything biological, interfered with carbonation. Clays and silts, if present in excess, blocked the pores that allowed lime mortar to breathe. Salts dissolved in sand could migrate to the surface of finished walls, creating unsightly efflorescence, or worse, crystallizing within the mortar structure and causing it to crumble. The process of sand selection involved washing, sieving, visual inspection, and tactile assessment, rubbing the material between fingers to feel for clay contamination, tasting it to detect excessive salt. These tests seem primitive. They were remarkably effective. Archaeological analysis of medieval mortars consistently shows aggregate quality exceeding what careless modern practice achieves. The medieval mason could not measure particle size distribution, but he could tell good sand from bad with his hands and tongue, and he understood that the invisible quality of his materials determined the visible survival of his work. Chapter 8. The Ratio of Resilience. Medieval mortar recipes varied by region, by application, by the specific properties of local materials. But across centuries and continents, one ratio appears with remarkable consistency. 1 part lime to 3 parts sand by volume. This proportion is not arbitrary. It represents an empirical optimization that modern laboratory analysis confirms as structurally ideal. Too little sand, and the mortar shrinks excessively during carbonation, producing networks of cracks that weaken the material. Too much sand and insufficient lime exists to coat all particle surfaces, leaving unbonded aggregate that crumbles under stress. The 1.3 ratio provides enough lime to fully surround every sand grain, while incorporating enough aggregate to minimize shrinkage. But ratio alone does not produce quality mortar. The mixing process matters equally. Lime putty and sand must be combined thoroughly, not merely stirred, but beaten, folded, worked until no visible streaks of unmixed material remain. Medieval masons describe the correct consistency as similar to butter. Smooth, plastic, able to be spread with a trowel, but stiff enough to stay where placed without slumping. The tool for achieving this consistency was called a larry, a long-handled hoe-like implement used to chop and turn the mortar in a mixing trough. Proper mixing could take hours. Insufficient mixing produced mortar with weak spots, areas where sand clumps remained surrounded by pure lime that would shrink and crack. The temptation to stop early, to declare the material ready before it truly was, explains many of the medieval mortar failures that did occur. Quality demanded patience at every stage. The lime burner's fire, the slaking process, the sand selection, the mixing, and then, once applied, the years-long wait for full carbonation. At no point did the process permit haste. The material itself enforced its own timeline. Chapter 9. The Application That Time Forgot. A medieval mason applying mortar worked with constraints no modern construction worker would accept. Fresh lime mortar cannot freeze. Water within the material expands upon freezing, disrupting the crystalline structure before it forms. This meant construction in northern Europe effectively stopped between November and March. Buildings rose only during the warm months. Stone by stone, course by course, each layer permitted to cure before the next was added. The application technique itself was specific. Mortar was not simply slathered between stones. First, the stone surfaces were thoroughly wetted. Dry stone wicks moisture out of fresh mortar, preventing proper adhesion and causing the surface to cure too quickly. Then mortar was applied in quantities slightly exceeding the joint width. The stone was pressed into position, squeezing mortar outward. This squeeze-out was not trimmed flush immediately. Instead, it was permitted to stiffen partially, then pressed back into the joint using a tool called a jointer, a process that compacted the mortar's surface, closing pores that would otherwise permit water penetration. The timing of this jointing was critical. Too soon, and the soft mortar smeared uselessly. Too late, and the surface had begun carbonating, becoming too hard to compress. The window was typically 2 to 4 hours after application, depending on temperature and humidity. A skilled mason developed instinct for this timing, pressing a thumb against the mortar's surface, feeling for the specific resistance that indicated readiness. The final step was curing. Fresh lime mortar requires moisture to carbonate. The chemical reaction consumes water, and if the surface dries too quickly, carbonation halts, leaving soft, weak material behind. Medieval masons protected fresh work with damp cloths, straw coverings, or repeated misting with water. Structures under construction were draped in wet sacking during hot weather. This extended curing continued for weeks, sometimes months, ensuring that carbonation penetrated fully through the joint depth. The process was labor-intensive beyond modern imagination. It was also why medieval mortar work survives centuries, while modern cement pointing fails within decades. Chapter 10. The Additive Secrets. Not all lime mortar was simple lime and sand. Medieval craftsmen developed an extensive pharmacopoeia of additives, materials that modified mortar properties for specific applications. The knowledge of these additives represented closely guarded professional secrets, passed within guilds and family traditions, rarely committed to writing. Some have been lost entirely. Others survive in fragmentary references that modern researchers struggle to interpret. The most widely documented additive was pozzolan, volcanic ash named for the Italian town of Pozzuoli, where Romans first recognized its properties. When mixed with lime, pozzolanic materials trigger a chemical reaction that creates calcium silicate hydrate compounds, the same binding agents that form in Portland cement. Pozzolanic lime mortars set faster than pure lime mortars and develop strength even underwater, where ordinary lime cannot carbonate due to the absence of atmospheric carbon dioxide. Roman engineers used pozzolanic concrete to construct harbor facilities, aqueducts, and the Pantheon's dome. Medieval builders continued the tradition wherever volcanic ash was available, or substituted crucite brick dust, which provided similar silica compounds. But pozzolans were only the beginning. Historical records mention dozens of other additives. Animal blood, added to mortar for waterproofing. The proteins coagulated during carbonation, filling pores with an organic sealant. Milk, particularly the casein-rich remainder after butter churning, provided similar protein modification. Egg whites improved workability and adhesion. Beer, malt, urine, organic compounds that affected setting speed, final hardness, or resistance to specific environmental conditions. Some additives seem bizarre until modern chemistry explains their function. Others remain mysteries. A 14th century Italian manuscript describes adding the ash of burned bones mixed with honey and the juice of certain plants to mortar intended for exterior sculpture. The specific plants are not named. The technique has not been replicated. The sculptures, protected by this unknown formulation, have survived 6 centuries of Italian weather with minimal degradation. Chapter 11. The Murder of a Material. Portland cement was patented in 1824 by Joseph Aspdin, a bricklayer from Leeds. The name referenced Portland stone, a prestigious limestone used in major English buildings, implying that the new material would provide equivalent quality. This was marketing, not chemistry. Portland cement and lime mortar share almost nothing except their calcium origin. The production process for Portland cement requires kiln temperatures exceeding 1,400 degrees Celsius, far hotter than lime burning. At these temperatures, calcium oxide reacts with silica and alumina compounds to form calcium silicates, which set through hydration rather than carbonation. The hydration reaction is fast. Initial set occurs within hours, workable strength within days, full cure within weeks. This speed was irresistible to an industrializing construction economy. Projects that once required years could be completed in months. Labor costs dropped. Construction schedules tightened. By the end of the 19th century, Portland cement had effectively displaced lime mortar in new construction throughout the industrialized world. The transition was not evaluated. It was not questioned. It was simply economically inevitable. The consequences took longer to appear. By the 1920s, historic buildings repointed with Portland cement began showing damage. The cement, impermeable to moisture, trapped water inside walls. Freeze-thaw cycles split the stone. Salt crystallization caused spalling. Within decades, masonry that had survived centuries began deteriorating faster than ever recorded. The conservation community raised alarms. They were ignored. Portland cement was cheap, fast, and modern. Lime mortar was slow, expensive, and associated with a primitive past that the 20th century was eager to transcend. The knowledge of traditional lime work survived only in isolated pockets. A few elderly craftsmen, a handful of specialized conservation projects, academic researchers cataloging what the industry had abandoned. The mainstream construction trades forgot that lime mortar ever existed. Chapter 12. The Price of Forgetting. Venice is sinking, not primarily because of rising seas, though that contributes, but because of well-intentioned restoration work conducted throughout the 20th century. When cement mortar was applied to medieval buildings designed for lime, moisture movement patterns changed catastrophically. Salt deposits concentrated at new locations. Brick and stone that had remained stable for 500 years began disintegrating within 5 decades. The Venetian case is extreme but not unusual. Across Europe, medieval cathedrals, castles, and historic structures suffer ongoing damage from incompatible modern repairs. The original lime mortar joints survived centuries of weather. The cement repairs fail within years, taking adjacent original material with them. A 2006 study by English Heritage estimated that cement repointing had caused more damage to British historic buildings in the 20th century than all the weathering of the previous 9 centuries combined. This is not opinion. This is measured degradation. Photographic records show structures that appeared stable in 1900 were improved with cement pointing in the 1950s and required emergency stabilization by the 1990s because the cement had trapped moisture that destroyed the very walls it was meant to protect. The irony is structural. Lime mortar is designed to be the weakest element in a masonry wall, deliberately sacrificial, accepting stress and damage that might otherwise crack the stone. When mortar erodes, it can be replaced without disturbing the masonry. Cement reverses this hierarchy. It is often harder than the stone it surrounds, forcing stress into the masonry itself. When damage eventually occurs, it is not to the easily replaced mortar, but to the irreplaceable historic fabric. The preservation community learned this lesson through decades of catastrophic failure. The mainstream construction industry still has not. Chapter 13. The Renaissance of Dust. Beginning in the 1970s, a small network of conservation professionals began systematically recovering traditional lime technology. Gerard Lynch, whose career started with that mysterious Yorkshire barn, became one of the movement's central figures. He spent decades analyzing historic mortars, interviewing elderly craftsmen who retained fragments of traditional knowledge, experimenting with production methods abandoned for over a century. The challenges were immense. Commercial lime production had shifted entirely to products optimized for agricultural use, not construction. The long-aged lime putty preferred by medieval masons sometimes matured for years before use, developing working properties that fresh material cannot match, was simply unavailable. Sand suppliers had standardized on washed, rounded material ideal for concrete, but wrong for traditional mortars. Even the tools had disappeared. No manufacturer produced traditional pointing irons or mixing larries. Conservation professionals fabricated their own equipment or adapted modern tools imperfectly. Training was nearly impossible, because almost no one remained alive who had worked with lime mortar as standard practice rather than historical curiosity. Lynch developed curriculum for passing on recovered knowledge. He established workshops where new craftsmen could learn techniques that the previous 2 generations had never encountered. He published research that documented not just what medieval masons did, but why it worked, connecting traditional practice to modern material science in terms that contemporary architects and engineers could understand. The effort has been partially successful. High-quality lime products are now available from specialist suppliers. A generation of conservation craftsmen has been trained in traditional methods. Building codes in many countries now require compatible materials when repairing historic masonry. But the larger construction industry remains committed to Portland cement. The speed advantage is too significant. The cost advantage too compelling. Lime mortar has returned from near extinction, but only to a niche. Chapter 14. The calculation that changes everything. In 2018, a team at MIT published a carbon life cycle analysis comparing Portland cement production to traditional lime mortar. The results inverted a century of assumptions about modern material superiority. Portland cement manufacturing is one of the most carbon-intensive industrial processes on Earth. The extreme kiln temperatures require massive fossil fuel consumption. The chemical reaction itself releases carbon dioxide, roughly 900 kilograms of CO2 for every ton of cement produced. Global cement production accounts for approximately 8% of all anthropogenic carbon emissions. If the cement industry were a country, it would be the third largest emitter in the world, behind only China and the United States. Lime mortar production also releases carbon dioxide. The calcination of limestone drives off CO2 just as in cement manufacture. But lime mortar reabsorbs that carbon during its decades-long carbonation process. The calcium hydroxide binder literally pulls carbon dioxide back out of the atmosphere as it cures. The cycle is not perfectly closed. Fuel emissions during lime burning represent a net addition, but the overall carbon footprint of lime mortar is roughly 60% lower than equivalent Portland cement. And this calculation does not account for lifespan differences. A Portland cement structure lasting 50 years requires complete replacement, with full associated emissions. Within a single human lifetime, a lime mortar structure lasting 500 years amortizes its initial emissions across 10 times the service period. The per-year carbon cost of lime construction may be 20 times lower than cement construction. These numbers have begun to penetrate policy discussions. Several European countries now offer incentives for lime mortar use in appropriate applications. Research programs investigate hybrid materials that combine lime's breathability and healing properties with improved setting speed. The construction industry's Portland monopoly is facing its first serious challenge since the 19th century, not from a new material, but from the oldest one. Chapter 15. The Wall That Teaches. In the Scottish Highlands, on a wind-scoured hillside above Loch Ness, a training center operates in a restored medieval farmstead. Students come from across Europe: architects, engineers, conservation specialists, traditional craftsmen seeking certification in historic building methods. For 3 weeks, they live without modern construction materials. They burn limestone in a replica kiln, tending the fire through 72-hour cycles. They slake the resulting quicklime, learning to manage the violent exothermic reaction safely. They age the lime putty, mixing test batches to understand how maturation changes working properties. They select aggregate, washing and sieving local sand, rejecting contaminated material by hand. They mix mortar with traditional tools until their shoulders ache and their hands crack from alkaline exposure. And then they build a wall. A simple freestanding stone wall, perhaps 10 meters long and 2 meters high. Each student contributes sections. Each section uses mortar mixed to slightly different specifications. Varied sand ratios, varied additives, varied application techniques. The wall becomes a permanent teaching record. Returning students can examine their previous work, observing how different formulations weather and carbonate over years. The oldest sections of the training wall date to the program's founding in 1994. They have now experienced 30 years of Scottish weather. Freeze-thaw cycles, driving rain, salt-laden coastal winds. They remain sound. They show the characteristic slow strengthening of properly made lime mortar. The joints tighter and harder with each passing decade. Adjacent sections, built by students who cut corners or misunderstood instructions, tell different stories. Failed experiments stand alongside successes. The material itself demonstrating what works and what does not, more clearly than any textbook could. The training center produces perhaps 40 certified lime craftsmen per year. Across Europe, similar programs operate in Italy, France, Germany, Spain. The total annual output of traditionally trained lime workers probably does not exceed 300. The world needs millions of such workers if lime mortar is ever to move beyond conservation niche into mainstream construction. The gap between capability and need is enormous. The knowledge exists. The materials exist. The demand exists. What does not exist is the economic and institutional will to value longevity over speed, to accept that building well sometimes means building slowly. Chapter 16. The Mortar That Remembers. There is a wall in Oxfordshire, England, that has stood since 1129. Not an important wall, not part of a castle or cathedral. Just a boundary wall separating one farmer's field from another's, built when Henry I ruled England and the Second Crusade had not yet been conceived. For nearly 900 years, this wall has performed its simple function. Rain has fallen on it perhaps 300,000 times. Frost has attacked it through more than 80,000 winter nights. Generations of cattle have rubbed against it. Children have climbed it. Storms have battered it. Wars have raged within sight of it. The wall remains. The stones have not shifted. The mortar joints show no significant erosion. Archaeological investigation in 2011, conducted because the wall happened to lie in the path of a proposed road improvement, found that the lime mortar had achieved a compressive strength of 28 megapascals. For comparison, modern concrete for residential foundations typically specifies 25 megapascals. The wall exceeds structural concrete specifications using only lime, sand, and 9 centuries of patient carbonation. But compressive strength is not what makes this wall remarkable. What makes it remarkable is the continuity it represents, the direct material connection between a medieval craftsman's hands and the present moment. The man who mixed that mortar is unknown. His entire life is unknown. He left no records, no family name that survived, nothing except the work of his hands still performing its function 900 years after he pressed it between stones. The mortar remembers him. It remembers the quality of his materials, the care of his mixing, the precision of his application. Every aspect of his skill is encoded in the survival of his work. Modern cement does not remember. It cannot. The hydration reaction that gives cement its strength is fast, anonymous, industrial. No individual touch distinguishes one cement joint from another. The material performs identically whether applied by a master or an apprentice, with care or with haste. Quality control is statistical, not personal. Medieval lime mortar carries fingerprints. Literally, excavated mortar sometimes preserves actual fingerprint impressions from the craftsman who smoothed it. But also, metaphorically, the material is slow enough, demanding enough, particular enough, that it rewards skill and punishes negligence. The wall reveals its maker. What we build reveals us. For a century, we have built with materials that forgive carelessness, that set before skill can distinguish quality from haste, that fail uniformly regardless of the attention invested in them. We have gained speed. We have lost the architecture of consequence. And somewhere in Oxfordshire, a 900-year-old wall still stands, asking a question we have not yet learned to answer. What are we building that anyone will care about in 900 years? The mortar remembers everything. The question is whether we are making anything worth remembering.